Hi, how are you doing today? My name is Lonnie Palama, and I'm going to teach probably one of the problems that is more difficult for high school students, a quantitative problem, no doubt. And this problem tends to have a lot of difficulty in terms of college students, let alone high school students. But let me go ahead and present this to you. The problem that I'm talking about is in the area of stoichiometric quantitative problems. The specific type of problem is finding and calculating the limiting reactant, calculating also the excess reactant, that reactant that will be left over after the chemical reaction, calculating an unknown mass that is produced by both the limiting and excess reactant, and fourthly, how much of the product of the original given amount of the excess reactant is left over. So we've got 4 different problems that we're solving within this one. So let me begin. I'm going to identify the chemical equation that we're going to use. The first one is in fact aluminum, and that is a solid, plus oxygen, and that's gas, and that's going to yield or produce aluminum oxide, Al2O3. Now the first step in any of these types of problems, especially a limiting reactant, is balance the equation. So in fact we're going to balance this. When we balance this, note the coefficients that are added, and the coefficients go from left to right, 4, 3, 2, in fact, identify a balanced equation, reactants balanced with the product. Okay? First step. Second step is, let's identify what the problem is, and then from that we're going to identify the given, we're going to identify the unknown, and then proceed forward. Okay, the problem states this. It states that aluminum metal will react with diatomic oxygen to produce aluminum oxide. In this problem, they state that the given amount of the 2 reactants, and I'm going to specify the given by identifying a G above those reactants, and I'm also going to specify the amount in the problem that's given, which is 50 grams of aluminum and also 50 grams given of the oxygen. The unknown I'm going to specify with the U, which is the aluminum oxide. And ultimately, one of the solutions that we're looking for is in fact the mass of the aluminum oxide. Okay, after we've done that, we note that this particular problem, both for the reactants that are involved as well as the product, both have masses. So typically on these types of problems, hey, we need to calculate what the molar mass is of the reactants and products. So let's go ahead and proceed. Okay, so I'm going to write in here molar mass. And while I'm thinking about it, hey, let's switch colors. Molar mass. Okay? And the molar mass that I am looking for, we're obviously, now when we are calculating our molar mass, of course we want to have available our periodic table and identify what the molar masses of both the reactants and products. Aluminum's molar mass, in fact, is 26.98 grams per mole. Okay, that's the first reactant. The second reactant, which would be diatomic oxygen, which in fact is 32 grams per mole. And then the product, or the unknown of the product, which is the aluminum oxide, has a molar mass of approximately 102 grams per mole. We're good to go at this point. We've identified what the molar masses are. Okay, what's our next step? Our next step, and I'm going to use a different color here. Our next step is to identify the number of moles of the reactants based on the amounts that are given. So let's proceed. Okay, let's move this up so we can see. All right, we note that aluminum we were given, on the aluminum side, we were given 50 grams. Okay. On the oxygen, also we were given 50 grams. Scoot that down. Now we want to divide this in order to calculate the number of moles of that given 50 grams for either by their molar mass. Hence the reason why we calculated the molar mass at the beginning. So divide this by its molar mass, which is 26.98. The oxygen by 32, and let's get a value. Okay? Now the value for the aluminum, in fact, comes out to 1.853 moles. Okay? The value for the oxygen comes out to 1.562 mole also of oxygen. Again, let me extend this so we can have a little more board here. These are the actual number of moles that are calculated based on the given. What's our next step? Well, the next step is we take our smallest mole value, which in this case is 1.562, and we divide both of these. Essentially what we want to do is we want to get a ratio of what do we have here. So let's divide both, starting with the aluminum, divide by 1.562. The oxygen, divide again by itself, 1.562. And let's get a ratio of numbers between those two. And we, in fact, we identify it here so we keep the numbers straight here on the side. The values that we get on the aluminum side after division is 1.186. And for oxygen, of course, we're going to get 1. Our next step. The next step is to compare this to the actual mole ratio in the chemical equation. Now, when we go back, let's take a quick look here so you can see that. The mole ratio is the relationship between the coefficients of the aluminum and the oxygen. So let's go back down, let's take a look. We're comparing the mole ratio. With the mole ratio of, let me write it down here. The mole ratio of 4 to 3, in essence, is the same as 1.333 to 1. And now let me move this up here so we can compare these two different ratios. So I am comparing A to 1.3331 to B. That's what I'm comparing. Now, let's do this by inspection. This is what I identify inspection. We use this in mathematics, but we also use this in chemistry. When I compare these, this is what it tells me. This particular value of what we have, 1.186, is less than the 1.333 that we actually need in terms of the mole ratio, the balanced equation. The oxygen, we have plenty of oxygen, 1 to 1. But what we don't have enough of is the aluminum at the top. And so hence we've already solved two of the solutions that we need. One, which one is the limiting reactant, and the second one is which one is the excess reactant. Let's identify those. So two of the solutions here are in fact, the aluminum is the limiting, and I'm just going to put limiting R for limiting reactant, whereas the O2 is the excess. Note that I oftentimes will abbreviate this as excess reactant. Okay, so two solutions. What's our next process? Well, the next process is to, in fact, do what they call a mole to mass problem, such that we can identify what is the number of grams that is produced with aluminum oxide. This is a mole to mass type problem. Well, let's take this at hand. It's a mole to mass. Okay? Well, the mole value that you and I are going to use is in fact going to be the original mole value that we calculated several steps before. And let me circle this to identify that. This 1.853 mole value is the value that we will use as our starting point to calculate what the mass of the product or the aluminum oxide will be. So let's go ahead, let's go on down and let's identify what we have here. So I'm going to, again, this is it is a mole to mass problem. Again, mole to mass is another type of stoichiometric problem. Note that this is part of the limiting reactant calculation. So let's take our mole value, which happens to be 1.853 mole, and that's my first step. Well, the second step is identifying and multiplying by the mole ratio of the unknown aluminum oxide to the known, which is aluminum, and that mole ratio happens to be 2 to 4. And I'll just identify that as a fraction. The next step, in order to move from moles to mass, we must multiply by the molar mass of aluminum oxide, which in fact, as we already calculated at the beginning, was actually 101.96 grams per mole. Multiply that. Hence, the mass that we get comes out to 94.46 grams of aluminum oxide that is produced as a result of 50 grams of aluminum and 50 grams of oxygen. Our third solution right here. That's the third solution. We're almost there. One other solution. The next one is we've got to do the same type of problem with a mole to mass, with the unknown being the oxygen reactant. And again, the known, of course, would be the other limiting reactant. So let's go ahead and do that. And of course, this will be the last section. So we are, in fact, doing a mole to mass. And again, remember that we have to use the limiting reactant mole value, which happens to be 1.853 from the limiting reactant. Okay. We then, of course, want to do the mole ratio, multiply times 4, the unknown to the known. Oxygen had a 3 coefficient, aluminum had a 4, so hence we multiply times that mole ratio, oxygen to aluminum, or 3 to 4. And then, of course, we need the molar mass of oxygen, or O2, which happens to be 32 grams per mole, per 1 mole. After calculation, we will, in fact, get 44.47 grams of O2 used. This is the number of grams of oxygen that is in fact used right here. Okay? Well, guess what? We started with 50 grams. So if we started with 50 grams, but we only used approximately a little over 44 grams, let's do a difference on that and we will calculate how much of the excess reactant, in this case oxygen, how much is left over. So let's go ahead and do that calculation. I'm going to use another color pen so we in fact can distinguish this. Okay, we started with 50 grams. Okay, we actually used, this is what we used, 44.47 grams. So let's subtract 44.47 grams. And in fact, the solution will in fact be the amount of 5.528 grams not used or in excess. Solution 4. And so hence, that is how we do a limiting reactant calculation. And we thank you.